Hi, folks. Today we're going to talk about gambling, games, and decision theory. Broadly, we're going to talk about game theory. So, game theory is quite fun. And so, game theory is the study of decisions and strategies, the study of strategic interaction. And so, philosophically, should we make decisions which help the individual, or should we make decisions which help the whole? And if we think that we should make decisions which support the whole, why do we keep making decisions which support the individual? Well, typically in game theory, we focus on interactions involving multiple people. There's a similar field called decision theory, which focuses more on the options of the individual. Game theory is sometimes thought of a subset of decision theory. But we're going to explore a lot of different things. And we're going to start with just the idea of games. And so we all know what games are. They're the things we play. We will focus on a few different types of games when talking about them today. And so there's a few common strategy games, such as tic-tac-toe, Connect Four, or chess. There are games of chance, such as gambling with dice, cards, or roulette. And then there's game theory. And in game theory, we focus less on these types of games, but they do give us insight into what strategies we might try and consider. And so let's start with tic-tac-toe. If you don't know tic-tac-toe, it's a fun one. Ask somebody around you. Tic-tac-toe is a fairly straightforward game. Given a 3x3 grid, two players go one at a time, placing X's and O's. The first player to get 3 in a row wins. If the board fills up before then, it is a tie. We say that a game like tic-tac-toe is a solved game, meaning the outcome is predetermined if players play rationally. In tic-tac-toe, there is no reason to ever lose. There's only a handful of possible moves, and once you know all the moves, you know how to win and how not to lose. And so while it is a solved game, when playing against the unaware, there is a winning strategy. The goal is to make it so that you have 2 opportunities to win at the same time. And so one winning strategy is begin in one corner, and if they play in the middle, play in the opposite corner. Most other moves they would make would lead to your winning. And we can see all of the different other things that could happen right here. If you go second, it is highly unlikely that you will win, but you can always lead to a tie. Connect Four is another turn-based strategy game in which individuals take turns dropping colored tokens into an array. The game is won if an individual manages to get 4 in a row. To the right, we can see that yellow won. As with tic-tac-toe, Connect Four is a solved game. There is a guaranteed winning strategy for whoever plays first. That said, do not look it up. It takes all the fun out of the game if you know how to win every time. Chess, on the other hand, feel free to look up. Chess is a much more complicated game with variations such as Shenki and Shogi in China and Japan. It dates back to at least the 7th century in India and Persia. Modern chess is played on an 8x8 board with a variety of pieces, each with their own moveset. The game is won when one player places the other in checkmate. The conditions of checkmate are the player is attacking the enemy king, and 2, there is nothing the opponent can do to prevent the king from being taken. And so that's the goal. Currently, chess is an unsolved game. Though with recent advancements in quantum computing, this may soon change. Instead, we focus on strategies in chess. So things like trying to control the center. If your pieces are in the middle of the board, they have more opportunities to attack. Another option is protecting the king. If your opponent can't get to your king, then they can't win. Another option is assigning values to pieces. And so using different weightings on points, you can determine when it is advantageous to take a piece. These strategies kind of speak to some of the different game structures. And so in a game, there's always some number of players who are playing the game. That's the first thing that we can recognize. In these games that we just talked about, there were 2 players, but we can envision a game with 1 person or a game with 20 people. Players may play one at a time or simultaneous, or perhaps they play whenever they feel like it. Play may be a strong word. It might not be very fun. And so, yeah. A game has rules and a winning condition which players are trying to achieve. Winning in chess is very different from winning in tic-tac-toe, but winning is the ultimate goal of a game. Also, there are strategies to achieve a winning outcome. Some games are solved and winning can be certain. Other strategies do not guarantee a win, but can get one closer to winning. For instance, in chess, assigning numerical values to your pieces can be a good strategy. And this idea of assigning numbers is something we're going to see quite a bit. That said, before we get into game theory, let's talk about games of chance, expected value, and gambling. And so gambling is a game of chance, often refers to a simple structure. A game is played in which a random event may occur. An individual places a wager or bet on a particular event occurring. And if the event doesn't occur, they lose their wager. If the event does occur, then they are returned their wager and additional funds of the same amount, or of some amount. It won't always be the same amount. While games such as poker can involve two or more players, we're going to focus on simpler structures involving a single person and wager. And to do so, we're going to talk about expected value. And so the expected value of a wager is what we expect on average to get in return for a given wager. And so if we let P of E be the probability of an event happening, and P of not E be the probability of the event not happening, we can let W of E be the amount you receive if the event occurs, and let L of E be the amount you lose if the event doesn't occur. Then the expected value is going to be equal to P of E times W of E minus P of not E times L of E. Basically, what's the probability of winning times your winning amount minus the probability of losing times your losing amount. And so here's a simple game. Given a coin flip, you can call heads or tails. If you wager $10 and win, you will receive $8. If you lose your $10. In this case, the expected value of $10 wager would be 0.5, because it's 50% likelihood that you're going to get $8, minus 50%, so 0.5, times losing $10. In this case, you would have an expected value of -1. This does not mean that you will lose every time, but that on average, if you play long enough, it will typically average a $1 loss for every round you played. And so to explore this a little bit more, we're going to play European roulette. Recall roulette. A ball rolls around a wheel and eventually settles on a location. An individual places a wager on an event, and if that event occurs, they receive their bet back and some amount of money. If they lose their wager. Let's calculate expected values. And so the table to the right shows all of the betting options in European roulette. European roulette only has one green value, and so that would be this 0 up here. We will use this to calculate expected values. A $10 wager on an individual value, such as lucky number 21, and note I put a chip on lucky number 21 so we can see what that looks like. Well, it will have a 1 in 37 probability of occurring, which means that the probability of it not happening would be 36 out of 37. If you win, you get your wager back and 35 times your wager. This means the expected value on a $10 wager of an individual number would be 1/37th of 350, because you would get $350 if you win, minus 36 out of 37 that you lose 10. Calculating this, you get a -0.27. This means in the short run, you might win a lot of money. But if you play long enough, you should average a loss of about 27 cents for each play. Well, let's try a different wager. Let us now suppose that we instead bet $10 on getting a red value. And so I moved the chip over here to red. Note from a probability perspective, it would be the same as betting on black, odds, evens, 1 to 18, or 19 to 36. Anything in this column is going to give you the exact same thing. A $10 wager on red will have an 18 out of 37 probability of occurring. If you win, you get your wager back and an amount equal to 1 times your wager. This means the expected value on a $10 wager of red is 18 out of 37 times 10 minus 19 out of 37 times 10, which is negative 27 cents. Note, it's the exact same expected value. And so whether you bet on 21 or you bet on red, your expected value is still negative 27 cents. Now let's suppose that we instead bet $10 on getting a 1, 2, 4, or 5. What you can do is put the chip on the corner of those 4 values, and that makes it so that if you get either of the or any of those 4, then you're going to get your wager back and some amount back. In this case, a $10 wager on the 4 corners will have a 4 out of 37 probability of occurring. And if you win, you get your wager back and an amount equal to 8 times your wager. This means the expected value on a $10 wager of a 4 values is, again, negative 27 cents. No matter where you're betting, it's going to be negative 27 cents for a $10 wager. While the expected values are all the same regardless of how you bet, the potential earning is quite different. Let's compare 3 bets on red versus 3 bets on number 21. In betting $10 on red 3 times, you could win up to $30, but it is more likely that you will be up $10 or down $10. It's also possible you could be down up to $30 also. In betting $10 on number 21 3 times, you could be up $1,050, but it is much more likely that you will be down $30. There is a 33.7% chance that you will have won at least once in your first 15 rolls, and a 50% chance that you will have won at least once in your first 26 spins. The house will always win in the long run, but it is possible to win in the short run. Let's compare it to American roulette. And so the key difference with American roulette is instead of 1 green spot, there are 2 green spots. And so a $10 wager on an individual value will have a 1 in 38 probability of occurring, but you will still only receive 35 times your wager. This means the expected value on a $10 wager ends up being negative 52 cents. You expect to lose money twice as fast in American roulette. And so if you are ever given the option, make sure to double check. And if there's 1 green spot, go with the roulette table that has 1 green spot. If you go with the one that's got 2 green spots, you should expect to lose money twice as fast. So why gamble? In any casino, the games are designed so that you lose in the long run. In the long run, the expected value will ensure a net win for the casino. That's how they are able to stay afloat. As an individual placing a wager, while your long term is guaranteed to be a loss, in the short term, you could win a lot of money. With a single bet of $100 in roulette, you could walk away from the table with $3,600 after a single spin or roll. If you play long enough, you will lose all your money, though. And given this information, some general guidelines if you are planning to gamble in a casino. 1, do it for fun, but do not expect to walk away a winner. And 2, be prepared to lose and determine how much you're willing to lose before beginning. When I play, I usually go for the long odds. The expected return is the same, but the likelihood of a big, meaningful win is much higher. Also, I like playing craps, but I never, ever remember the rules, and so I got to look it up each time. Similar to roulette, we have the lottery. And so the California Lottery, Powerball, or Mega Millions all follow the same principle as roulette. The expected value of a wager is always negative. With the long odds comes the potential for a life-changing win. Much like a casino game, it's less about winning and more about having fun or building up a little hope to get you through the day. Which leads us to game theory. Let's talk about the prisoner's dilemma and Pascal's wager. So here is the prisoner's dilemma. Consider two criminals who have committed a crime together. The police don't have much to convict, and so they make an offer. If you confess to the crime and blame your partner, you will get a reduced sentence. And so if you confess and your partner doesn't, you get probation, and they will serve 20 years. If they confess and you don't, they get probation and you get 20 years. If you both confess, you will both serve 5 years. But if you both stay quiet, you will each serve only 1 year. You do not know what your partner will do. So what should you do? Well, this is where game theory comes in. In decision theory, we seek to determine what the best decision is for a given set of information. Often, we explore game theory in the context of decision theory, where we try to determine what a winning outcome might look like for a given set of players. The prisoner's dilemma is one of the fundamental examples of game theory. To explore the options, we will typically use a payoff matrix, a chart which shows what the outcomes will be for a given set of choices. We typically try to represent the outcomes as a number, and often the numbers will be different for each individual player, and the goal of each player is to maximize their outcome. And so usually, large numbers represent good outcomes for the player. Small values represent less good value or less good outcomes. And let's use this food example to try and understand what's going on. And so consider the payoff matrix to the right regarding a food decision. We have two players. We have Tommy and we have Bobby. Tommy wants to eat a burger. That's his first priority. But he would rather eat alone. He really doesn't want Bobby to tag along. Bobby likes eating with other people. More than anything else, he just wants to eat with Tommy. But he would rather eat a taco. His first priority, though, would be being with other people. And so looking over at this matrix that we have over here, this chart, the first value in each one of these boxes is representing the weight given to Tommy and what Tommy would prefer. Whereas the second value is telling us what Bobby would prefer. And so let's look at all these options. For Tommy, he's got the 10 over here, where his best case is where he is eating burgers and Bobby is eating tacos. For Bobby, Bobby's best situation is where Bobby is eating tacos and Tommy is also eating tacos. But that would be Tommy's absolute worst case. And for Tommy, he's saying he would have zero satisfaction from that because he doesn't want a taco and he doesn't really want to hang out with Bobby. And so the question becomes, what strategy will lead to the best results? Can we determine what is going to happen based on this matrix showing how much they would like to do each outcome? And so a dominant strategy is a move that provides a higher payoff regardless of how the other player plays. And so we can basically say in each case, is there a situation where Tommy will do better no matter what Bobby chooses? Or is there a situation where Bobby can pick one and it'll be better no matter what Tommy does? If a player has a dominant strategy, it is assumed that they will take that dominant strategy. All other players should then plan as though that player with a dominant strategy will utilize the dominant strategy. In this case, do either Tommy or Bobby have a dominant strategy? Well, let's look at it. And so let's look at Tommy here. And so Tommy, he can choose either burgers or he can choose tacos. If Tommy chooses a burger, if Bobby chooses burgers, let's suppose that Bobby chooses burgers. Well, if Bobby chooses burgers, then Tommy could choose burgers and have a 7 enjoyment, or he could choose tacos and have a 4 enjoyment. In that case, the 7 is more, so it would be better for Tommy to choose burgers. If Bobby chooses tacos, well, then Tommy would again have a better option of choosing the burgers. And so in this case, Tommy has a dominant strategy. He should choose burgers. For Bobby, does Bobby have a dominant strategy? Well, let's say that Tommy chooses burgers. If Tommy chooses burgers, well, then Bobby would either choose burgers and get a 7 here, or he would choose tacos and get a 4. And so if Tommy chooses burgers, it's better for Bobby to choose burgers. If Tommy chooses tacos, well, then it would be better for Bobby to choose tacos, because if Tommy chose tacos and Bobby went with burgers, that would be his worst case scenario. But if Tommy chooses tacos and Bobby chooses tacos, that would be his best case scenario. And so in this case, Bobby's decision is really dependent on Tommy's. Either it's to go with the burgers and be in this upper left category, or to go with tacos and be in this bottom right category. So how do we determine what's going to happen? Well, Tommy has a dominant strategy. Since Tommy has a dominant strategy, we should expect him to go with it. And so there's no reason for Tommy not to choose burgers in this situation. Either way, he's getting the better option. Because Tommy is choosing burgers, Bobby should assume Tommy is going to choose burgers. And so since Bobby's assuming Tommy's going with burgers, it would be in his best interest to also go with burgers, because then he would get this 7 value instead of this 4 value. So because of this, we can see the most logical outcome is for both of them to end up having burgers. Now let's apply this to the prisoner's dilemma. In the case of the prisoner's dilemma, both prisoners have a dominant strategy. And so let's suppose that prisoner B confesses, and let's just assume that he confesses. Well, if he confesses, then the better option for prisoner A would be to confess also, because then he'd get 5 years instead of 20 years. What if prisoner B remains silent? Well, if prisoner B remains silent, it's still a better option for prisoner A to confess, because then he'd get 0 years instead of 1 year. And so in this case, the dominant strategy for prisoner A is to confess. And same for prisoner B. The better case is to confess. And so if they both confess, well, they're both following their dominant strategy, and they would both get 5 years. But when we look at everything, we can see that's not the best outcome. If we were trying to do what's best for the whole, that would probably be this 1 year and 1 year. That would certainly be better than the 5 years for each. And so the question is, why are we saying that this dominant strategy is what's most likely to happen? Well, we call this type of situation a Nash equilibrium. And so a Nash equilibrium is a case where neither player has incentive to deviate from their strategy, such as in the prisoner's dilemma. The Nash equilibrium does not guarantee the actual best outcome for all players. In the case of the prisoner's dilemma, if they could be trusted to keep silent, they would get the best combined result. Both serving 5 years, though, is the Nash equilibrium, but far from the best outcome. One of the greatest challenges of humanity is finding ways to not end up in a Nash equilibrium. And when we think about it, what the Nash equilibrium is really telling us is it's telling us what's best for the individual. But what is best for the individual might actually not be what's best for the individual. And so we have a hard time trying to get around that. Here's another example: probability in games. And so sometimes instead of 2 players, a decision must be made based on the likelihood of an uncertain event. And so consider the case to the right where we have Laura, and Laura wants to go to the lake, but only if it's sunny. If it's raining, she would much rather be at home, but there's only a 30% chance of rain. After applying her weights to each event, should she go to the lake or should she stay home? And so let's look at this. Looking at this, we can see that it's a 70% chance of sun, a 30% chance of rain. In this case, the lake, well, her ideal would be to go to the lake and for it to be sunny. But if she goes to the lake and it rains, she is going to be the most unsatisfied. Uh, if it's sunny, uh, she would much rather be at the lake than be at home, because if she's at home, she's just going to be thinking about the lake. But if it rains, she would much rather be at home, because then she would be so thankful that she didn't go to the lake. And so, how do we determine what the best option is? Well, we have percents. And so what we can do is we can determine the expected value. And so this is a case where we use the expected value to make the decision. If she goes to the lake, her expected value is 70% likely that she's going to get a 10 and 30% likely that she's going to get a 2. Multiplying and adding that, we get an expected value of 7.6. If she stays home, her expected value is going to be 70% of 4 and a 30% of 6. So that would be a 4.6. Even though there is the chance that it's going to rain and that that'll be the worst situation for her, the expected value is significantly higher for her to go to the lake. And so she might be she might be concerned about the rain, but logically her best option is to go to the lake. Along these lines is the idea of Pascal's wager. This is one of the early ideas which led to the development of game theory. And so in the 16th century, Blaise Pascal tried to apply this same type of logic to Catholic theology. Should a person believe in a Christian God and follow Catholic doctrine or not? This is known as Pascal's wager. And so let me explain Pascal's version. In Pascal's wager, or in Pascal's version, if God exists and you believe, you get infinite reward. While if you don't believe, you get infinite punishment. If God doesn't exist, at most, it's a finite gain or loss of your life. And so Pascal concluded that the only option that made sense was belief in Catholicism, because belief leads to the possibility of infinite reward. If these are equally likely, then we could say 50% of infinity minus 50% of C is going to give you something. Whereas if you don't believe, 50% of negative infinity plus 50% of C will give you your expected value of negative infinity. And so expected value for believe is infinite, and expected value for don't believe is negative infinity. There are issues with Pascal's wager, but at least it introduced the idea of game theory. And so if we want to extend Pascal's wager, it's deeply, deeply flawed. But probability and calculus weren't as well understood at the time. And we're talking 17th century. Pascal assumed that there was a 50-50 chance that his interpretation of Catholicism was what would lead to eternal happiness, which is a stretch on many fronts. It also raises questions about the valuation of a life. Is a life a finite value? Ultimately, in trying to explore Pascal's wager, you need to understand how indeterminate forms work. And it quickly becomes clear that the answer isn't as easy as Pascal thought. Which leads us to high-level game theory applications. And I wrote tinfoil hat time because most things in the world actually follow game theory fairly clearly, and we can actually model them using game theory. But it's going to get weird. And so our first application is capitalism. Capitalism, in many ways, is an application of game theory. The game is a simple one. Get money, turn money into power, repeat. The question is, how do we use money to make more money? Decisions of corporations which focus on profit often lead to systemically negative results. And while society can rapidly advance, there's always a cost. And as consumers, we often find ourselves trapped in a Nash equilibrium, which is truly unfortunate. Purchasing from the largest corporations, and so Amazon and Walmart and whatnot, is frequently financially the best option. They can get the lowest prices because they have the largest inventory and whatnot. The consequences of that are structural. So there's fewer small businesses, there's fewer employment opportunities, lower median wages, more homelessness, greater class disparities. These are all real consequences of this Nash equilibrium. Another application is the stock market. The stock market is a game and one which is the core of our economy. Companies issue stocks to raise capital. Occasionally, they may provide dividends to stockholders. Individuals buy and sell these stocks in the hope of selling at a higher price than they purchased. At that point, it's a game. How do you determine which stocks will do better, and how well can you play the game to increase your earnings? Another one is political gerrymandering. And so gerrymandering is the act of redistricting a region to have a greater influence for one political party. Every 10 years, the US does a census of its citizens, and districts are redrawn, often by the parties in power. In redrawing the regions, they can play a game to optimize the likelihood of their own re-election or redistribute power in whatever way they see fit. Political action. Oh, another good one. The way a bill becomes a law is highly political, and those who know how to play the political game are able to do amazing and horrible things. In any House of Congress or elected or appointed body, the ultimate goal is to get the necessary votes to push forth policy. It's a game. It's a question of how to manipulate individuals and legislation to get the policy approved. Another one, global warming. We understand the mechanisms of global warming fairly well. Additional carbon in the atmosphere leads to minute changes in global temperatures. Minute changes in global temperatures lead to large-scale chaotic weather patterns, which occur more frequently. It is a very clear application of chaos theory. The problem is individuals, corporations, and governments still stand to benefit from adding carbon to the atmosphere. And as long as that's the case, things aren't going to change. And so we, again, need to find ourselves a way out of that Nash equilibrium. Language and theology, and cultures for that matter. When we think of modern languages and theologies, they didn't always exist, and they've been naturally competing for millennia. It's not like one language is attacking another language or anything silly like that. It's more that we have people who are joining a population and people who are leaving a population. And so in both cases, it becomes a question of how languages and theologies are spread. How are new members introduced to the population, and how are members removed from the population? In the case of Latin or Pythagoreans, not all languages or religions stand the test of time, and the process by which new languages and religions gain prominence is the structure of game theory. Final thoughts. While graph theory and topology taught us about how things are connected and grouped together, game theory teaches us about how decisions are made amongst these groups. The structural implications of game theory is the background noise of our lives, as every decision made seeks to accomplish some goal, and we are all forever trapped in the Nash equilibrium of their consequences. Yeah, that's one of the hard bits. And so the question is, how can we get out of those Nash equilibriums? And if anyone has an answer, let me know. With that, I'll let you get to work exploring where you find game theory and these types of decisions in the real world. Good luck, folks.